I'm Dr. T, and welcome to my whiteboard. So today I'd like to talk to you about energy and change. So you may be familiar with specific heat and calorimetry, but in those cases we're usually thinking of, say, a solid piece of metal giving off heat to some water, or maybe vice versa, or it could be really any old thing. But there's no change necessarily involved. If there's change, we're going to have to start changing up our equations a little bit, and we need a new term, and that's called enthalpy. Enthalpy has a working definition, not a perfect one, but a working definition of the energy of order, or the energy of structure. The idea here is that when you form structure, you form bonds, things, say, click into place, metaphorically or literally, then energy is no longer as necessary. It's a lower energy state. So it would take energy to break the bonds or to get them out of their order. Enthalpy is that energy, the amount of energy that would be given off when that order is created or consumed when you have to try and break apart that order. Enthalpy gets the abbreviation delta H, and it will almost always have some kind of subscript. Delta H fusion in this particular case for freezing. Delta H reaction for reacting, vaporization for vaporizing. It can be chemical, physical. It just needs to be a change. And we'll have enthalpy of. You will also quite often see it as heat of. Now, there is a caveat when I'm describing this. Make sure you read the fine print. In some cases, the delta H is describing what's taking place with your system. In that case, exothermic would be negative. And usually if you see it written as enthalpy of, that's going to be the case. If you see it as heat of, it could be either the energy with respect to the system, but it could also be with respect to the surroundings. So heats of combustion, even though this is an exothermic process, are usually written as positive numbers because it's reference to the surroundings, not to the system. So make sure you're paying attention to the context and to those minus signs, because nice inconsistencies is a wonderful way to make it even more complicated. Different systems do different things, different groups of people have different preferences, and unfortunately you sometimes get to straddle different groups. Now, delta H is going to have units that are going to be energy units, typically kilojoules, and amount units. And here's another catch where you have to make sure you read the fine print. Q will either equal mass times the delta H, or it will equal the number of moles. N sub A refers to number of moles, although quite often you will see it just simply as N. N for number in this case. So your units, you want to pay attention. This would be probably kilojoules per gram, whereas this one would be kilojoules per mole. It's a very easy mistake to look it up, think it's one, and, well, it was the other one, and you just needed to convert. Speaking of which, this actually looks a lot like a conversion factor. You've got two different units, and we can use it just like a conversion factor. So let's go over here. I have an example where we are freezing some water, or allowing some water to freeze, depends on which way you want to think about it, which is, strangely enough, an exothermic process. It actually makes perfect sense. As the water is freezing, you have to suck the heat out of it to get it to freeze. Sounds like an exothermic process to me, even though we wouldn't really call this thing hot. Okay, so I've got water freezing, yay. Fancy terms. It's not a chemical change, but I can still do a chemical reaction for it, even though it's not chemical. Yeah. I've got my heat of fusion for my freezing of water. In that case, it's 6 kilojoules per mole. I've got my question. Hey, I've got 32 grams of water. How much energy is it going to give off? And I've got some nice good old-fashioned dimensional analysis. Grams to moles, because that's in moles. I got to make sure that I get my grams and moles lined up. Grams won't cancel with moles without my nice formula weight. Okay, and then boom, that's the amount of energy it's giving off. Pretty straightforward, actually, compared to that evil algebra when we dealt with calorimetry. Oh wait, we're not really done with calorimetry. Great. Now, we can do calorimetry with this one. This gives me a Q. A Q, yay! But, so is calorimetry. So what we can do is we can ask a slightly different question. I can say, hey, I've got my calorimeter. It has a reaction going on inside of it. In this particular case, it's an aqueous reaction in a water-based calorimeter. It doesn't have to be. You can have calorimeters that have no water in them whatsoever. And those are actually quite common and quite popular. So I've got this, and I need some statistics, some information. Okay, so I've got this reaction. It's reactants to products, because this is a fancy reaction. Okay, it's just some nice generic terms. Specific heat of the water, this is going to be my surroundings. I've got the temperature change of the water. I don't have a temperature change of the reaction, though. Reactions that are in the water, they're governed by this equation, not the previous calorimetry equation. And what I want to find is the delta H of this particular reaction. By the way, Rxn stands for reaction. Now, I have the moles of R for this particular reaction. I'm going to have 2 moles in this particular case. Okay, time for some math. So I'm going to start out, and I'm going to combine this equation with my calorimetry equation. So Q equals mCs delta T. That's this half. It's surrounding, so it's going to be a minus number. And then here's my reaction, which is my system. And, well, I'm going to just simply use this particular one. I could use that if this number was in grams. So either way. So I've got this sorted out. I plug in my numbers. I do some algebra. This isn't nearly as vicious as it was beforehand. Of course, if I wanted to be a bit obnoxious, I could be solving for TF. That's always fun. And then I get my answer. But here's the catch we always have to be very careful of when doing this type of work. Specific heats are almost always in joules per gram, degree C, or Kelvin. In this case, the Kelvin or degree C is interchangeable. Whereas delta H's typically are going to be in kilojoules. These changes are going to have much more energy involved. So kilojoules makes much more sense. That said, joules and kilojoules aren't the same thing, so we have to make sure that we work with one and not try and work with both at the same time, because you can't. You got to get them into the same type of units. So, yay, we've got ourselves some energy. Quick point. These get to be pretty big numbers, actually. That reaction with 2 moles of whatever my stuff is made a pretty decent change. Generally speaking, when it comes to either physical changes like phase changes like we had over here or chemical reactions like this, delta H's are going to be quite large. And so if you've got a phase change or a chemical reaction, you can produce a lot of energy or consume a lot in the process. Just kind of keep that in mind that those can be pretty big deals. With that said, have a wonderful day.